Let us now discuss electromagnetic wave equation in differential form. So last time we discussed the Maxwell's equation, the four equations, the Gauss law of electricity, Gauss law of magnetism, Faraday's law and Ampere-Maxwell law. So these are the four Maxwell's equations. So using these equations we can now obtain a equation for electromagnetic waves. For this, let us remember one of the relations in mathematics, that is, if you take a vector a bar, then you can write curl of the vector a bar as gradient of the divergence of a bar minus del square, that is the Laplacian of a bar. So this is the relation for the curl of a vector. So now let us apply it on the Maxwell's third equation, Faraday's law, as well as the Maxwell's fourth equation, that is Ampere-Maxwell law. So here we have curl of electric field, and we can now apply the curl of electric field vector. So according to this relation, it becomes equal to gradient of divergence of E bar minus del square, the Laplacian of E bar. Now we can use the Maxwell's first equation, that is the Gauss law of electricity, and we can write the divergence of E bar. So it is divergence of D bar is equal to rho. So therefore divergence of E bar is equal to rho by epsilon. So I can write therefore the divergence of E bar is equal to rho by epsilon in this equation. And Maxwell's third equation we have taken here, that is curl of E bar is equal to minus dou B bar by dou T. So therefore the equation 2 can be written as, so by substituting for the divergence of E bar as rho by epsilon and curl of E bar as minus dou B bar by dou T, we can write this as the curl of E bar is equal to grad of rho by epsilon minus del square E bar. Now let us take the Maxwell's fourth equation, that is Ampere-Maxwell law. So Ampere-Maxwell law gives us the curl of magnetic field vector B bar is equal to mu times J bar plus dou D bar by dou T. Again applying the relation, that is the curl of the vector, so that we apply it on this now. That is, first let us take the electric field. Curl of E bar is equal to minus dou by dou T of curl of B bar. So that is applying it on the Maxwell's third equation. So we get this. Now the curl of magnetic field vector B bar can be written using the fourth equation. Here we can write it as mu times J bar plus mu times dou D bar by dou T. So I got equation 5 here, which is this, and we have got equation 7 here, which is this. That means using the mathematical relation, we have got curl of electric field as like this. That is using this relation, and we substituted using the Maxwell's first equation as that is divergence of E bar as rho by epsilon, that we have got here. That is the equation 5. Now using the Maxwell's fourth equation, in the Maxwell's third equation we have got it here, that is the curl of E bar is equal to minus dou by dou T of mu J bar plus mu dou D bar by dou T. Now combining equation 5 and 7, now we can write the gradient of rho by epsilon minus del square E bar is equal to minus dou by dou T, that is, or you can take mu here common outside, so that means minus mu dou J bar by dou T minus mu epsilon dou square E bar by dou T square. Here we have written d bar as epsilon E bar. Therefore epsilon is coming out here. So rearranging these terms in this equation, I will take this minus del square E bar to the right hand side, and this minus mu epsilon I will keep it here only, but this part minus mu dou j bar by dou t I transfer to this side. So I get del square E bar minus mu epsilon dou square E bar by dou t square is equal to mu dou j bar by dou t plus gradient of rho by epsilon. So this is the equation we get here. This is called as the wave equation for electric field vector E bar. So here we see this is the second derivative of the electric field vector E bar, and this is the space derivative, this is the time derivative, second derivative of electric field with respect to time t. So this part represents a wave equation. This part represents the sources, the source responsible for this electric field wave. Now if we take the vacuum, in vacuum you know that there is no charge, therefore charge density is 0, and therefore current density J bar is also 0. That means in this equation 8, the right hand side becomes 0, rho is 0, and charge density, the current density vector J bar is 0. So right hand side is 0, but also you can see that in the vacuum mu, the permeability becomes mu naught, that is permeability of vacuum, and epsilon, the permittivity becomes the permittivity of vacuum, that is equal to epsilon naught. So making these changes in the equation 8, we can write the equation 8 now for vacuum as del square E bar minus mu naught epsilon naught dou square E bar by dou t square is equal to 0. So this is called as the equation for the electric field vector in vacuum. Now this is similar to any wave equation, and if we compare it to the wave equation, the velocity of the wave can be written as 1 by square root of mu naught epsilon naught, that is this term here. So the velocity of the wave is given by 1 by square root of mu naught epsilon naught. So mu naught and epsilon naught are constants. We know that mu naught is permeability, epsilon naught is permittivity of vacuum. So these constants, if we substitute for this and calculate, we get the velocity of the electric wave here as 3 into 10 power 8 meter per second. Now whatever we have done for the electric field vector, the same can be repeated for the magnetic field vector B bar or H bar. So when we do that, we get a similar equation for as we got for electric field vector. So we get del square H bar minus mu naught epsilon naught dou square H bar by dou t square is equal to 0. So this is the equation, the wave equation for the magnetic field vector H bar. So this now proves that there is a wave, that is electric and magnetic wave, which is produced due to the changes in the electric field and magnetic field, and we get a wave that is moving together, that is called as the electromagnetic wave. And the velocity of both these waves, we can see that it is given by this, which is equal to 3 into 10 power 8 meter per second. That means it is same as the velocity of light. So it implies that these electromagnetic waves are moving with the velocity which is same as the velocity of light, and maybe these electromagnetic waves are same as the light waves. So that was the prediction given by Maxwell, and it was proved later on, and we now know that the light waves are actually the electromagnetic waves.